Alright, so the last problem of this extra practice for our propositional logic will have three pieces to it. So suppose all of the following status reports are true. Processor B is not working and processor C is working. Processor A is working if and only if processor B is working, and at least one of the two processors, A and B, is not working. So the first thing we're asked to do is to essentially write all of those statements in terms of symbols, where A is working, B is working, and C is working. So I'm going to write those right next to their statements. So processor B is not working and processor C is working. So it's not the case that B is working, so we have not B. And C is working, so just regular C. So then we have processor A is working, if and only if processor B is working. Now remember, the if and only if is our biconditional, the kind of double arrow. So also remember that this essentially goes to two different things. This is technically saying A implies B, and we would also have B implies A. So it'll be good to think about it in both ways for the next part of this, but technically, as stated, it would be the biconditional. And then at least one of the two processors, A and B, is not working. So essentially it has to be the case that either A is not working or B is not working. So it'll be the case that either A is working, essentially not the case, sorry, it'll be not the case that either A is working or B is working. So of course, if you think about that in terms of De Morgan's, this would be equivalent to not A and not B, but technically, as stated, the one on the left follows a bit more from the wording of the statement. At least one of the two processors is not working. It is not the case that one of them is working. So it's not the case that either A is working or B is working. So now that we have those three statements, and again, so now I'm going to erase the De Morgan's one because we're gonna focus on just having that. So given the statements in part A, we want to write proof sequences for the following. So no, you might not need to know all the givens you might not need to, use all of the givens in each case. So essentially we have too many givens in a way because we're trying to prove three separate things and we might need some of the givens for one and not for the others. So we're essentially going to do three separate proof tables. We're asked to prove two different things. So let me set up my proof tables first. Let me just draw those out really quick. And so our givens are going to be the things that we just wrote down. The thing that we are told is true. So in this case, we are going to list them as 4 because we're going to break that biconditional up into its two pieces. Because for the sake of a proof table, it is easier to just, it's not even a fact of easy, it's the fact that we're going to want to possibly use one of the ways and not the other to help our proof. So I'm going to just write down the given for all of these before we tackle one. So what we're going to do is we're going to try to prove these things that we're asked. So the first thing we're going to do is we're going to try to prove that A is not working. And then we're going to try to prove that B is not working. And then we're going to try to prove that C is working. So these are all givens. Let me just zoom in a little bit to make sure that I'm writing small enough for us to be able to conclude what we need to conclude. So what we want to conclude in this first one is we want to conclude that A is not working. So we want to somehow conclude not A. Okay? So if we go over to our rules and think of things that could help us figure out a not A, maybe the moduses are looking kind of good. Maybe simplification might look kind of good. So let's kind of see what we're working with here. Now, in this case, since we're looking for a not A, we're probably not going to use the first statement because it doesn't have an A in it. So notice that 2, 3, and 4 all have A's in them, so they're probably going to be more likely to help us out a little bit. So one thing I notice is that I have a not and an A in the same line. They're not together yet, but there's a not and an A in line 4. So if I did actually do De Morgan's law, I know I kind of noted that they were equivalent. If we actually do use De Morgan's law on line 4, can I just get that not A off of it? Yes. Since we now have an and statement, remember whenever you have an and statement, you can always, essentially throw away one of them, if you will. So we can essentially say not A by simplification. And that would be from line 5. And we're done that one. We wanted to conclude not A. We did it. We didn't even need 1, 2, and 3. So, now one thing I do want to talk about in case it's confusing is, say you thought that maybe you wanted to use implication on line 2. That would get you not A or B. But getting you there doesn't really help because it's an or and not an and, so there's nothing we can really do with it. So really getting you there doesn't help in any way. So while it's technically a rule you could use implication on line 3 too, but it just doesn't really get us anywhere. But that's one thing with these proof tables, is that sometimes you kind of need to go down a rabbit hole and realize that that way is wrong before you realize what the right way is. But if we move on to the next one we wanted to conclude that B is not working, so not B. Now I want to try to get a not B out of this, so I'm probably, actually all 4 of those are very fair game and all possible because they all have a B in it. So now there's possibly a few other ways you could do this, but if you notice that we got a not B by the De Morgan's last time, so if we kind of go the same way and use De Morgan's law on line 4, it's almost like we can do the exact same thing and just get rid of the not A. But again, remember, as we've talked about in kind of the other videos, if you want to use simplification correctly, the thing that you're simplifying to should be in the front. So we need to use commutativity first on line 6 before we can pull off the not B. And then that would be by simplification on line 6. And sorry, I've messed up these lines. It should be 4, 5, and now 6. And so that got us our conclusion, but I actually want to do another process that could work as well to show you again that there are sometimes multiple ways to do these. Now technically this would start off the same way with De Morgan's on line 4. So essentially this is saying anything past the givens I'm redoing. And we could essentially recreate what we did in the last one and just get not A by simplification. And then notice that I have not A, and I also have B implies A from line 3. And that actually sets me up for a modus tollens. I have B implies A and not A, which would end me with not B, would result in not B. That would be a modus tollens on 6 and 3. So there's technically more than one way you could go about this. So it's not exactly the case that everyone's proofs are going to be exactly the same. Sometimes you might find a proof that is slightly different than your neighbor's. So just be aware that sometimes there are multiple ways to go about these. So now we're on to the last one where we want to conclude just regular old C. So that actually probably means that we're not going to use 2, 3, and 4 of our givens because none of those have an A in it. a C in it. So that probably means that we need to somehow manipulate the first one to just get C. Now notice that that is an and statement. Whenever you have an and statement, you always want to keep in the back of your mind that you can use simplification. And what do we want? We want a regular C, which is already in there. So actually, if we just flip-flop that over using commutativity on line 1, then we're done. Use simplification on line 5, and we've got our desired result. So that's one thing with these rules, is that whenever you have an and, you should definitely keep into the back of your mind our simplification rule. And if you ever have, things by themselves, you always want to think about addition. So simplification and addition, while to be quite honest, they were used quite a lot in this extra practice. And I find that they're not used a lot in most other proofs, but they are very useful. So while a lot of the other rules get a lot more airtime, if you will, when it comes to a lot of the other proofs we'll see, it's definitely good to keep those in the back of your mind because they can be really helpful if you just have these and or statements that you can just manipulate right away. But that is the end of this extra practice. If you have any questions about this practice, about these inference and equivalence rules, please let me know. This is a very complex topic. It takes a lot of time and a lot of practice to get good at it. So if you have any questions, feel free to let me know.